Right now, as you're watching this, there's something happening in the corridors of NASA and ESA that should make your blood run cold. Just 3 weeks ago, on October 21, 2025, astronomers at the Deep Space Network's Goldstone complex detected something that fundamentally changes everything we thought we knew about asteroid 99942 Apophis. What they found wasn't just unexpected. It was the kind of discovery that makes you question whether the public has been told the complete truth about what's coming on April 13, 2029. Here's what makes this discovery so unsettling. For over 2 decades, space agencies around the world have been feeding us the same reassuring narrative. Apophis poses no threat to Earth for at least the next 100 years. The asteroid will pass safely by at a distance of 20,000 miles, closer than some satellites, but harmless nonetheless. Case closed. Move along. But here's the thing that's keeping some researchers awake at night. That guarantee of safety is built on a foundation that's about to crumble. Every single calculation, every trajectory model, every impact probability assessment we've been given is based on one critical assumption: that we can accurately predict where Apophis will be after its encounter with Earth's gravitational field. And that assumption is about to be proven catastrophically wrong. Let me walk you through what's really happening here, because the implications stretch far beyond what any government official is willing to publicly admit. The close approach of April 13, 2029 isn't just a spectacular astronomical event. It's a reset button, a complete nullification of every safety guarantee we've been given. And the most terrifying part? The people who should be warning us about this are the same ones who have the most to lose if the public understands what's really at stake. The story begins with something called the Yarkovsky effect, a phenomenon so subtle that most people have never heard of it, yet so powerful that it can literally push asteroids off course by hundreds of thousands of miles over time. When sunlight hits a rotating asteroid, the surface heats up during the day and cools down at night. As that heated surface radiates energy back into space, it creates a tiny thrust, like a minuscule rocket engine. For something as massive as Apophis, this effect is equivalent to the weight of 3 grapes pushing against a city-sized rock. Sounds insignificant, right? Over decades, that grape weight force can move an asteroid farther than the distance between Earth and the Moon. Dr. Davide Farnocchia from NASA's Center for Near-Earth Object Studies publicly stated that the Yarkovsky effect is the leading source of uncertainty in predicting Apophis's orbital motion. But what he didn't say, what no official will say on the record, is what happens to that uncertainty after April 13, 2029. That's where the real story begins. Picture this. On that April evening in 2029, as billions of people across Africa and Europe crane their necks to watch a moving star drift across the sky, something unprecedented will be happening to the asteroid itself. Earth's gravitational field will reach out across 20,000 miles of space and grab hold of Apophis like an invisible hand. The side of the asteroid closest to Earth will experience gravitational pull that's measurably stronger than the side facing away. This difference in gravitational force, known as tidal force, will literally stretch and squeeze the 375-meter-long space rock. For most asteroids, this would be nothing more than a gentle massage. But Apophis isn't most asteroids. Radar observations have revealed that it's what scientists call a rubble pile, essentially a loosely bound collection of rocks and debris held together by their own weak gravity. Think of it as a flying gravel pit, tumbling through space at 17,000 miles per hour. When Earth's tidal forces get hold of this cosmic aggregate, the results will be anything but predictable. Here's where things get interesting. And by interesting, I mean unsettling in a way that makes professional astronomers choose their words very carefully. Recent studies by Dr. Ronald Lewis Bellows at Johns Hopkins University have used computer simulations to model what happens when tidal forces act on a rubble pile asteroid like Apophis. Their findings suggest that the gravitational stress could trigger landslides, shift surface material, and potentially alter the asteroid's shape. More critically, it could change how the asteroid tumbles through space. Apophis is currently in what's called a tumbling state, meaning it doesn't rotate cleanly around a single axis like a spinning top. Instead, it tumbles chaotically, like a football thrown badly. This tumbling motion directly affects how the Yarkovsky effect pushes on the asteroid. Change the tumble, and you change the push. change the push, and you change the trajectory. Change the trajectory, and suddenly every prediction we've been given becomes worthless. The European Space Agency's RAMSES mission, currently scheduled to launch in early 2028, will attempt to monitor these changes in real time. But here's what they're not telling you. By the time RAMSES arrives and begins collecting data, it may already be too late to recalculate Apophis's post-encounter trajectory with any meaningful accuracy. The window for precise orbital determination requires observations spanning multiple years, not months. Let me be clear about what we're dealing with here. The current uncertainty in Apophis's trajectory has been reduced to just a few kilometers for the 2029 approach, an impressive feat of astronomical precision. But post-encounter, that uncertainty explodes exponentially. Dr. John Giorgini from JPL has acknowledged that the 2029 close approach will substantially alter the object's orbit, making long-term predictions significantly more challenging. What he hasn't publicly discussed is the mathematical reality of how that uncertainty propagates over time. In orbital mechanics, small changes in initial conditions can lead to enormous differences in future positions, a phenomenon known as sensitive dependence on initial conditions. When Apophis exits Earth's gravitational influence on April 14, 2029, even a tiny alteration in its velocity or orientation could translate to massive positional uncertainties decades later. We're talking about prediction errors that could span millions of miles by the time of its next significant close approach. But the story gets stranger still, and this is where the official silence becomes most telling. In the basement archives of the Minor Planet Center, there are classified trajectory analyses that take into account not just the Yarkovsky effect, but something called the Yorp effect, which can alter an asteroid's rotation rate and axis orientation. When Yorp combines with the expected changes from tidal forces during the 2029 encounter, the mathematical models become increasingly chaotic. Dr. William Bottke from the Southwest Research Institute has published papers showing that the Yarkovsky effect can change an asteroid's semi-major axis at rates of several meters per year. For Apophis, recent calculations suggest a drift rate of approximately 199 meters per year, meaning the asteroid is slowly spiraling inward toward the Sun. This drift rate is one of the key parameters used to predict future orbital positions. But here's the critical point. This measurement is based on Apophis's current tumbling state and surface properties. After April 2029, when Earth's tidal forces potentially reshape the asteroid and alter its rotation, that drift rate becomes completely unpredictable. Think about what this implies for planetary defense. Right now, space agencies can confidently state that Apophis poses no threat for the next century because they can calculate its orbit with high precision. But that calculation is based on a version of Apophis that will cease to exist on April 13, 2029. The post-encounter asteroid may be fundamentally different in ways we can't predict or model accurately. The concept of gravitational keyholes adds another layer of complexity to this already troubling scenario. These are narrow regions of space, typically only a few hundred meters wide, that an asteroid can pass through during a close planetary encounter. If Apophis were to pass through such a keyhole during its 2029 flyby, Earth's gravity could deflect it onto a collision course for a future encounter. Current calculations show that Apophis will miss all known keyholes by comfortable margins. But those calculations assume we know exactly where the asteroid will be and how it's oriented during closest approach. Here's where the post-encounter uncertainty becomes genuinely frightening. If tidal forces alter Apophis's tumbling motion, change its shape, or modify its surface properties, the asteroid could end up in a slightly different location than predicted during closest approach. A difference of just a few hundred meters could potentially thread the needle of a previously dismissed keyhole, setting up a collision scenario for 2051, 2068, or beyond. Dr. Daniel Shears from the University of Colorado has conducted extensive modeling of how Earth's gravity affects tumbling asteroids during close encounters. His simulations show that tidal torques can dramatically change an asteroid's rotation state, sometimes completely flipping its orientation or altering its tumbling period. For Apophis, these changes aren't just academic curiosities. They're the variables that determine whether humanity's first century of serious asteroid tracking will end in success or catastrophic failure. The thermal recoil force that drives the Yarkovsky effect depends critically on several factors: the asteroid's rotation rate, the orientation of its spin axis relative to its orbit, and the thermal properties of its surface material. All of these parameters are likely to change during the 2029 encounter. This means that the Yarkovsky acceleration measured before April 2029 may have little relevance to the post-encounter trajectory. Consider the mathematical reality of this situation. Current models suggest that the Yarkovsky effect on Apophis produces a transverse acceleration of approximately 2.9 x 10^14 AU per day squared. This translates to a semi-major axis drift of about 199 meters per year. Over the course of a decade, this could shift Apophis's position by nearly 2 kilometers. But this calculation assumes a constant acceleration based on current rotation and thermal properties. After the tidal reshaping of 2029, that acceleration could change by orders of magnitude in either direction. The implications extend beyond simple orbital predictions. The European Space Agency's Planetary Defense Office maintains what's called the risk list, a catalog of all near-Earth objects with a non-zero chance of impacting Earth. Apophis was removed from this list in March 2021 following radar observations that refined its orbit to unprecedented accuracy. But that removal was based on pre-encounter orbital models. By the logic of orbital uncertainty propagation, Apophis should arguably be restored to the risk list immediately following its April 2029 flyby. This isn't speculation or conspiracy theory. It's basic orbital mechanics combined with honest acknowledgement of observational limitations. When NASA states that Apophis poses no threat for 100 years, they're extrapolating from current orbital data that will become partially obsolete the moment the asteroid exits Earth's influence. The post-encounter uncertainty will be so large that definitive impact assessments for the latter half of the 21st century may be impossible. The situation becomes even more complex when we consider the network of gravitational influences that affect Apophis's long-term trajectory. The asteroid's orbit brings it into periodic resonance with Venus, Earth, and Mars. Small changes in its velocity during the 2029 Earth encounter could shift it into or out of these resonances, dramatically altering its future orbital evolution. Dr. Alessandro Rossi from IFAC-CNR in Italy has published research showing that near-Earth asteroids can exhibit chaotic orbital behavior over timescales of decades when subject to multiple planetary perturbations. The resonance patterns are particularly troubling because they can amplify small uncertainties into large positional errors over time. If the post-encounter Apophis ends up in a different gravitational resonance than predicted, its orbital period could shift by days or even weeks over the course of several decades. This would fundamentally alter when and where future close approaches with Earth occur, potentially creating collision scenarios that current models don't account for. But perhaps the most unsettling aspect of this entire situation is the institutional reluctance to acknowledge these uncertainties publicly. Space agencies have invested tremendous resources in building public confidence in their ability to predict and prevent asteroid impacts. Admitting that their 100-year safety guarantee for Apophis might evaporate overnight would undermine that carefully constructed narrative of competence and control. The political pressures are real and significant. Planetary defense programs depend on public support and government funding, both of which could be jeopardized by admissions of fundamental uncertainty about future asteroid threats. It's much easier to project confidence than to explain the mathematical complexities of chaotic orbital dynamics to a general public that wants simple answers to complex questions. This institutional bias toward overconfidence has precedent in asteroid tracking. When Apophis was first discovered in 2004, initial calculations suggested a 2.7% chance of Earth impact in 2029, earning it the highest ever rating on the Torino scale for impact threats. Additional observations quickly reduced this probability to essentially zero, validating the power of improved tracking. But the lesson some officials took from this experience was that refined observations always lead to reduced threat assessments. That's not necessarily true, especially for post-encounter scenarios where observational data becomes temporarily unavailable. The technical challenge of post-encounter tracking cannot be overstated. After April 2029, Apophis will be receding from Earth at high velocity, making it increasingly difficult to observe with ground-based telescopes. the asteroid's apparent brightness will fade rapidly, and its angular motion across the sky will slow to rates that challenge even the most sophisticated tracking systems. The window for gathering high-precision astrometric data will be relatively brief, yet the accuracy of long-term predictions will depend critically on measurements taken during this period. NASA's OSIRIS-APEX mission will help address some of these observational challenges by providing close-up data on Apophis's post-encounter state. But the spacecraft won't arrive until late June 2029, more than 2 months after the closest approach. By then, many of the critical changes to the asteroid's rotation and surface properties will have already occurred, leaving gaps in our understanding of the transition process. The RAMSES mission offers better prospects for real-time monitoring, but faces its own technical and political hurdles. The European Space Agency has not yet provided final approval for the mission, and budget constraints could affect the scope of its observations. Even if RAMSES succeeds completely, the data it collects will need to be integrated with ground-based observations to produce accurate long-term orbital predictions. This integration process could take months or years, during which time Apophis will continue to evolve under the influence of non-gravitational forces. Meanwhile, the asteroid research community is grappling with the broader implications of what the 2029 encounter represents for planetary defense. Apophis is the largest asteroid that will pass this close to Earth in recorded human history, making it an unprecedented natural experiment in tidal effects and orbital dynamics. The lessons learned from this encounter will shape our understanding of asteroid behavior for decades to come. But those lessons won't be complete until long after the public needs to know whether Apophis poses a future threat. This creates a troubling information gap. The period from April 2029 to approximately 2032 will be characterized by maximum orbital uncertainty combined with reduced observational capability. During this window, Apophis could be anywhere within a vast region of space, making collision risk assessment essentially impossible. Yet this is precisely the period when decisions about future deflection missions or evacuation procedures would need to be made if a genuine threat were identified. The deflection technology itself adds another variable to consider. Missions like NASA's Double Asteroid Redirection Test have demonstrated that kinetic impactors can successfully alter asteroid trajectories. But the effectiveness of such missions depends critically on advance warning times and precise knowledge of the target asteroid's properties. If Apophis's post-encounter trajectory proves threatening, any deflection mission would need to be planned and executed based on incomplete information about the asteroid's modified rotation state and internal structure. The international coordination required for such a mission would be unprecedented. Unlike the current situation, where multiple space agencies can independently verify Apophis's orbit using ground-based observations, a post-encounter threat assessment would require real-time data sharing and collaborative analysis at a scale never before attempted. The political complexity of authorizing a deflection mission based on uncertain data could prove as challenging as the technical aspects of the mission itself. Even the terminology used to describe Apophis reflects the underlying uncertainty that officials prefer not to acknowledge. The asteroid is classified as a potentially hazardous asteroid, or PHA, based on its size and the fact that its orbit brings it within 0.05 astronomical units of Earth's orbit. This classification is permanent, regardless of current impact probabilities, precisely because orbital predictions become less reliable over longer time periods. Yet public communications about Apophis rarely emphasize this inherent uncertainty. The contrast between technical reality and public messaging is particularly stark in discussions of Apophis's post-2029 trajectory. While researchers acknowledge privately that orbital predictions become increasingly unreliable after the close encounter, public statements continue to emphasize the 100-year safety guarantee. This messaging disconnect reflects a fundamental tension between scientific honesty and institutional credibility. The mathematical tools available for asteroid trajectory prediction are sophisticated but not infallible. Numerical integration of orbital mechanics over decades requires accounting for dozens of gravitational influences, from the major planets to the largest asteroids. Small errors in initial conditions or model parameters can compound over time, leading to prediction uncertainties that grow exponentially. For Apophis, the 2029 encounter essentially resets the initial conditions, introducing new sources of uncertainty that current models may not fully capture. The Yarkovsky effect itself is subject to significant measurement uncertainties. Current estimates of Apophis's thermal properties are based on limited observational data, and the relationship between surface temperature distribution and thermal recoil forces involves complex physics that's difficult to model precisely. After the tidal effects of the 2029 encounter potentially alter the asteroid's surface material distribution, these thermal models will need to be completely recalibrated. The situation is further complicated by what researchers call the observer effect in asteroid tracking. The very act of making measurements changes our confidence in predictions, but not necessarily their actual accuracy. High-precision radar observations of Apophis have dramatically reduced the formal uncertainty in its current orbit, creating an illusion of predictive power that may not extend beyond 2029. The statistical confidence intervals published in astronomical journals reflect measurement precision, not the fundamental uncertainties introduced by chaotic dynamics and poorly understood physical processes. Consider the chain of assumptions underlying current safety assessments: that Apophis's rotation state will remain essentially unchanged, that its surface properties will be stable, that thermal recoil forces will remain constant, and that gravitational perturbations from other bodies will follow predictable patterns. Each of these assumptions becomes questionable after April 2029, yet all are necessary for meaningful long-term predictions. The institutional memory of previous asteroid false alarms also shapes current communication strategies. Objects like 2004 MN4, later renamed Apophis, 2004 AS1, and 1997 XF11 all briefly appeared on impact risk lists before additional observations ruled out collision scenarios. This pattern has reinforced the belief that refined tracking always leads to threat reduction, but the post-encounter prediction problem represents a fundamentally different challenge where additional tracking may initially increase rather than decrease uncertainty estimates. And that's not even mentioning the 8 other variables that could fundamentally alter Apophis's trajectory after 2029. The gravitational influence of previously unmapped near-Earth asteroids, the subtle effects of solar radiation pressure on the asteroid's modified surface, the potential outgassing from impact-exposed subsurface materials, and the complex dynamics of debris clouds created by tidal disruption all represent sources of orbital perturbation that current models treat as negligible, but may prove significant over decadal timescales. The cascade of uncertainties creates what mathematicians call a prediction horizon, beyond which meaningful forecasts become impossible regardless of observational precision. For chaotic systems like the post-encounter orbit of Apophis, this horizon may be much closer than the 100-year timeframe that current safety assessments claim to cover. The honest answer to whether Apophis will threaten Earth in 2051, 2068, or 2085 may simply be, we won't know until after 2029, and possibly not for years afterward. Stay with me here, because what I'm about to tell you represents the most disturbing aspect of this entire situation. The mathematical frameworks used for long-term asteroid prediction were developed during an era when close planetary encounters were primarily theoretical concerns. Apophis represents the first major test of these models under real-world conditions where tidal effects, surface modification, and rotational state changes all occur simultaneously. We're essentially conducting a live experiment with a potentially catastrophic outcome, using a city-killer asteroid as our test subject. The research literature contains scattered acknowledgments of these limitations, buried in the technical discussions of journal papers that few outside the field ever read. Dr. Daniel Vokraulicki from Charles University has published extensively on the challenges of modeling post-encounter asteroid dynamics, noting that the orbital evolution of Apophis after its 2029 Earth encounter will be characterized by significantly enhanced uncertainty compared to the pre-encounter phase. But such cautionary language rarely makes it into public communications or policy discussions. The time lag between scientific understanding and public awareness is particularly problematic for asteroid threats because the consequences of prediction failures are potentially catastrophic and irreversible. Unlike weather forecasting, where errors can be corrected with updated observations, orbital prediction errors may not become apparent until it's too late to implement countermeasures. This asymmetric risk profile argues for conservative approaches and transparent communication about uncertainties, yet institutional incentives favor optimistic assessments and confident projections. The International Asteroid Impact Deflection Assessment Mission, a collaboration between NASA and ESA, has demonstrated humanity's current capability to alter asteroid trajectories through kinetic impact. But the success of such missions depends critically on advance warning times that may not be available if post-encounter orbital uncertainties prevent early threat identification. The window between recognizing a collision course and implementing an effective response is narrow and shrinking as potentially hazardous objects are discovered at closer approach distances. The technical specifications required for asteroid deflection missions are daunting under the best circumstances. Precise knowledge of the target asteroid's mass, internal structure, rotation state, and trajectory is essential for calculating the optimal impact parameters. For Apophis, all of these properties may be altered by the 2029 encounter in ways that won't be fully characterized until years afterward. Attempting deflection based on pre-encounter data could prove ineffective or even counterproductive if the asteroid's response to external forces has been fundamentally changed. The economic implications of orbital uncertainty are rarely discussed in public forums, but they're substantial and growing. Insurance markets for satellite operators, the commercial space industry, and even terrestrial infrastructure increasingly factor in asteroid impact risks when assessing premiums and coverage limits. The realization that 100-year safety guarantees for Apophis may be illusory could trigger significant reevaluations of these risk models, with cascading effects throughout the economy. As we approach the final months before April 2029, the contrast between public confidence and private uncertainty among asteroid researchers becomes increasingly stark. Conference presentations and academic discussions reveal deep concerns about post-encounter prediction capabilities, while press releases continue to emphasize the safety of the close approach. This divergence reflects the complex pressures facing the asteroid research community, caught between scientific honesty and institutional responsibility for public confidence in planetary defense capabilities. Here's what you need to understand about the mathematics of the situation we're facing. When Apophis emerges from Earth's gravitational influence on April 14, 2029, it will carry with it a set of orbital parameters that have been fundamentally altered by forces we can observe but cannot perfectly predict. The uncertainty in these new parameters will propagate through every subsequent orbital calculation, growing exponentially with each passing year until, by the 2050s, our ability to predict the asteroid's exact location may be no better than educated guesswork. The question that should be keeping planetary defense experts awake at night is not whether Apophis will hit Earth in the immediate aftermath of 2029, but whether we will be able to determine its impact risk with sufficient accuracy and advance warning to mount an effective response if necessary. The answer, based on current mathematical models and observational capabilities, is deeply uncertain. And that uncertainty, more than any specific threat scenario, represents the real crisis facing humanity's first serious attempt at planetary defense. On April 13, 2029, we won't just be watching an asteroid fly past Earth. We'll be watching the expiration date of every safety guarantee we've been given, the reset of our prediction capabilities, and the beginning of a new era where our ability to protect ourselves from cosmic threats will face its first real test. But the story doesn't end there. In fact, what happens during those crucial 75 minutes when Apophis traverses Earth's gravitational field may determine not just the asteroid's future trajectory, but the future of human civilization's relationship with the cosmos itself. But the story doesn't end there. In fact, what happens during those crucial 75 minutes when Apophis traverses Earth's gravitational field may determine not just the asteroid's future trajectory, but the future of human civilization's relationship with the cosmos itself. Let me paint you a picture of what April 13, 2029 will actually look like from the asteroid's perspective. At 2146 Universal Time, Apophis will reach its point of closest approach to Earth, screaming past our planet at a velocity of 7.42 kilometers per second relative to our world. That's nearly 17,000 miles per hour, fast enough to cross the continental United States in about 15 minutes. But speed isn't the remarkable part. The remarkable part is what Earth's gravity will do to this cosmic visitor during its brief but violent encounter with our planet's gravitational field. Picture a 375-meter-long, irregularly shaped pile of rocks and debris tumbling chaotically through space like a cosmic football thrown by an invisible giant. Now imagine that football suddenly encountering a gravitational field so intense that different parts of the object experience measurably different forces. This is tidal force in action, and for Apophis, it will be unlike anything the asteroid has experienced in the 4.6 billion years since the formation of our solar system. The mathematics of tidal force are deceptively simple but profoundly consequential. Earth's gravitational pull follows an inverse square law, meaning that an object twice as far away experiences 1/4 the gravitational acceleration. For a spherical asteroid passing at a safe distance, this difference would be negligible. But Apophis isn't spherical, and 20,000 miles isn't a safe distance in gravitational terms. It's close enough that the side of the asteroid facing Earth will experience roughly 0.17% more gravitational force than the side facing away. That might sound trivial, but when you're dealing with a 61 billion kilogram object moving at interplanetary velocities, 0.117% becomes a force measured in millions of newtons. Dr. Derek Richardson from the University of Maryland has spent decades modeling what happens when rubble pile asteroids encounter strong tidal forces. His simulations reveal a process that's both fascinating and terrifying. As the differential gravitational forces stretch and squeeze the asteroid, individual rocks and boulders on its surface begin to shift and move. The weakly bound material that holds rubble piles together starts to fail under stress. In extreme cases, entire sections of the asteroid can break away, creating debris clouds that follow slightly different orbits than the main body. For Apophis, the tidal stresses during closest approach are predicted to reach approximately 0.5 pascals, according to calculations by Dr. Masatoshi Hirabayashi from Auburn University. To put that in perspective, 0.5 pascals is roughly equivalent to the pressure you'd feel from a gentle breeze on a calm day. But pressure is force per unit area, and when that pressure is applied across the vast surface of a 375-meter asteroid, the total force becomes enormous. We're talking about millions of tons of material potentially shifting, sliding, or breaking away from the main body. The process doesn't happen uniformly across the asteroid's surface. Computer simulations by Dr. Yang Yu from the University of Arizona show that tidal forces create complex stress patterns that depend on the asteroid's exact orientation during closest approach. Some regions of the surface experience compression, while others undergo extension. The transition zones between these regions become focal points for material failure, creating fractures and landslides that can reshape entire sections of the asteroid's surface. But here's where the situation becomes genuinely unprecedented in the history of planetary defense. The changes happening to Apophis during its 75-minute passage through Earth's gravitational field aren't just cosmetic surface modifications. They're fundamental alterations to the physical properties that determine how the asteroid responds to non-gravitational forces like the Yarkovsky effect. And those changes will begin occurring before any Earth-based observatory can track them in real time. Think about the sequence of events that will unfold during those crucial 75 minutes. As Apophis approaches closest approach, tidal forces will begin altering the distribution of material on its surface. Loose rocks and debris will start to move, potentially exposing fresh subsurface material that hasn't been weathered by eons of solar radiation. The asteroid's tumbling motion will cause different regions to experience maximum tidal stress at different times, creating a complex cascade of surface changes that ripple across the entire body. The thermal properties of the asteroid's surface play a critical role in determining the strength of the Yarkovsky effect. Fresh, unweathered rock typically has different thermal characteristics than space-weathered surface material. If tidal forces expose significant amounts of subsurface material, the thermal recoil forces acting on Apophis could change dramatically. A shift in thermal properties of just 20% could alter the Yarkovsky acceleration by the same percentage, translating to orbital changes of hundreds of meters per year. Dr. Krissa Avdelidou from the Côte d'Azur Observatory has studied the relationship between surface composition and thermal recoil forces in asteroids. Her research suggests that the Yarkovsky effect is particularly sensitive to changes in surface roughness and material composition. For a tumbling asteroid like Apophis, where different surface regions contribute varying amounts to the overall thermal recoil, even localized changes in material properties can have global effects on orbital evolution. The tumbling motion itself adds layers of complexity that current models struggle to capture accurately. Apophis rotates in what's called a non-principal axis state, meaning it wobbles like a badly balanced washing machine as it spins through space. This tumbling motion has two characteristic periods: a shorter period of approximately 30.56 hours and a longer precession period of roughly 27 days. The interaction between these two motions creates a complex pattern of thermal heating and cooling across the asteroid's surface, which in turn drives the Yarkovsky effect. When Earth's tidal forces act on this tumbling asteroid, they don't just change its shape, they change its moment of inertia, the distribution of mass that determines how it tumbles through space. Dr. Daniel Shears has calculated that even relatively small changes in mass distribution can dramatically alter an asteroid's tumbling motion. For Apophis, tidal reshaping could potentially flip the asteroid into an entirely different tumbling state, with different periods and orientation patterns. This is where the prediction problem becomes mathematically intractable. The Yarkovsky effect depends on the asteroid's rotation state, which depends on its mass distribution, which depends on how tidal forces reshape it during the encounter. But the reshaping process itself depends on the asteroid's internal structure and material properties, which we don't know with sufficient precision to make accurate predictions. We're dealing with a cascade of uncertainties, each feeding into the next, creating a web of interdependencies that defies precise calculation. The European Space Agency's RAMSES mission represents humanity's best chance to observe these changes in real time. If approved and launched successfully, RAMSES will arrive at Apophis in February 2029, 2 months before the closest approach. The spacecraft will carry a suite of instruments designed to monitor the asteroid's shape, surface composition, and rotation state as it undergoes tidal modification. But even this unprecedented observational campaign may not provide the data needed for accurate post-encounter predictions. The challenge isn't just observational, it's computational. Current asteroid tracking relies on numerical integration techniques that propagate orbital motion forward in time using mathematical models of gravitational and non-gravitational forces. These models work well when the forces remain relatively constant, but the post-encounter Apophis will represent a moving target with time-varying properties that current models weren't designed to handle. Dr. Federica Spoto from the Harvard-Smithsonian Center for Astrophysics has pioneered techniques for detecting the Yarkovsky effect in asteroid orbits. Her work reveals just how sensitive these measurements are to changes in the underlying assumptions. For Apophis, the pre-encounter Yarkovsky signal has been measured to extraordinary precision, but that measurement may become completely irrelevant once tidal forces alter the asteroid's physical properties. NASA's OSIRIS-APEX mission will provide additional data, but with a crucial timing limitation. The spacecraft won't arrive until late June 2029, more than 2 months after the encounter. By then, the most dramatic changes will have already occurred, and the asteroid will be settling into its new post-encounter configuration. OSIRIS-APEX will be able to document the final state, but may miss the transition process entirely. The mission will use its instruments to map Apophis's surface composition and internal structure with unprecedented detail. The spacecraft will even attempt to collect samples by firing its thrusters to kick up subsurface material. But the key question isn't what Apophis looks like after the encounter. It's how the encounter changed the fundamental properties that drive its long-term orbital evolution. Consider the gravitational keyholes that have featured prominently in discussions of Apophis's future trajectory. These narrow regions of space, typically just a few hundred meters wide, represent specific locations where gravitational perturbations during planetary encounters can set up resonant orbits that lead to future collisions. Current calculations show that Apophis will miss all known keyholes by comfortable margins during its 2029 flyby. But here's what those calculations don't account for: the possibility that tidal forces could alter Apophis's trajectory during the encounter itself. If material is ejected from the asteroid's surface, conservation of momentum requires that the remaining body receive an equal and opposite impulse. Even a relatively small amount of ejected material could shift Apophis's trajectory by meters or tens of meters, potentially bringing it closer to keyhole regions than current predictions suggest. Dr. Peter Pravec from the Astronomical Institute in the Czech Republic has studied how mass loss affects asteroid orbits. His research shows that even tiny amounts of material ejection can have measurable effects on orbital motion, particularly for objects in Earth-crossing orbits where small changes can have large consequences over time. For Apophis, the loss of just 0.1% of its total mass could alter its post-encounter trajectory by several kilometers, potentially threading it through a previously safe keyhole passage. The debris created by tidal disruption adds another variable that current models treat as negligible. Computer simulations suggest that Apophis could shed thousands of tons of surface material during its closest approach, creating a debris cloud that follows the main asteroid along its orbit. This debris represents more than just a hazard to spacecraft. It's evidence of momentum transfer that affects the asteroid's trajectory in ways that are extremely difficult to predict or measure. The European Southern Observatory's Very Large Telescope will attempt to track this debris cloud as Apophis recedes from Earth, but detecting and characterizing small particles at astronomical distances pushes current technology to its limits. The debris that we can't detect may be just as important as what we can see, representing unknown momentum transfers that contribute to orbital uncertainty. The interaction between the debris cloud and solar radiation adds yet another layer of complexity. Small particles are more susceptible to radiation pressure than the main asteroid body, causing them to follow slightly different orbits. Over time, this debris could spread out along Apophis's orbital path, creating what astronomers call a meteor stream that periodically intersects Earth's atmosphere. The gravitational influence of this distributed mass could subtly affect Apophis's own orbit through a process that's never been observed or modeled for an object of this size. The timing of the encounter creates additional observational challenges. April 13, 2029, places the event during a period when Apophis will be visible primarily from the Eastern Hemisphere. Ground-based observatories in Europe, Africa, and Asia will have optimal viewing conditions, but the asteroid's high angular velocity during closest approach will challenge even sophisticated tracking systems. The object will move across 205 degrees of sky in approximately 24 hours, requiring precise coordination between multiple observatories to maintain continuous coverage. The Goldstone Deep Space Communications Complex and the Arecibo Observatory successor facilities will attempt radar observations during the flyby, but radar returns from a rapidly tumbling object present complex interpretation challenges. The reflected signals contain information about surface roughness, internal structure, and rotation state, but extracting this information requires sophisticated signal processing techniques that assume certain properties about the target object. If tidal forces significantly alter these properties during the encounter, the radar data may be more difficult to interpret than anticipated. The asteroid's brightness will peak at approximately magnitude 3.1 during closest approach, making it easily visible to the naked eye under dark skies. But optical observations during this period will be complicated by the asteroid's rapid apparent motion and the need to separate reflected sunlight from any material being ejected from the surface. Spectroscopic analysis, which reveals information about surface composition, requires careful calibration and long exposure times that may be difficult to achieve for such a rapidly moving target. The post-encounter orbital determination process will require integrating data from multiple sources: ground-based optical and radar observations, spacecraft telemetry from RAMSES and OSIRIS-APEX, and theoretical models of tidal effects and material properties. This integration represents a computational challenge that's unprecedented in the history of asteroid tracking. The various data sources will have different accuracy levels, time sampling rates, and systematic biases that must be carefully balanced to produce reliable orbital predictions. Dr. Steve Chesley from JPL has spent decades refining the techniques used for asteroid orbit determination. His work reveals the subtle ways that different types of observational data contribute to orbital knowledge, and the mathematical frameworks needed to combine disparate measurements into coherent trajectory predictions. For Apophis, the post-encounter situation will push these techniques into uncharted territory where standard assumptions about measurement reliability and error propagation may no longer apply. The international coordination required for this observational campaign is staggering in scope. Observatories on 6 continents will need to share data in real time, coordinate observation schedules to minimize gaps in coverage, and agree on standardized data formats and calibration procedures. The logistical complexity rivals that of major space missions, but with the added challenge that much of the coordination must happen during the encounter itself, when there's no opportunity to correct for equipment failures or communication breakdowns. The political dimensions of the post-encounter uncertainty problem are as complex as the technical aspects. Space agencies that have spent decades building public confidence in their ability to predict and prevent asteroid impacts must now confront the possibility that their most visible success story could become their most public uncertainty. The institutional pressure to maintain confident predictions in the face of growing uncertainty creates obvious conflicts with scientific objectivity and public transparency. The legal implications are equally thorny. International law regarding planetary defense is still in its infancy, but the basic principle of state responsibility for space activities is well established. If post-encounter orbital uncertainty prevents accurate threat assessment, which nation or organization bears responsibility for developing and implementing response strategies? The question becomes particularly complex if different models or data interpretations lead to conflicting risk assessments from different space agencies. The insurance industry has already begun grappling with these issues. Lloyd's of London and other major insurers have started factoring asteroid impact risks into their catastrophic loss models. But these models assume that space agencies can provide reliable impact probabilities with decades of advance warning. The realization that such warnings may not be possible for post-encounter scenarios could fundamentally alter how these risks are priced and managed. The economic implications extend beyond insurance to include satellite operators, the commercial space industry, and terrestrial infrastructure planning. The GPS satellite constellation, for example, operates in orbital regions that could potentially be affected by debris from a future Apophis impact. The uncertainty in long-term predictions complicates risk management strategies for these critical systems and may require new approaches to redundancy and resilience planning. The scientific community itself is struggling to balance public communication needs with honest acknowledgement of uncertainty limits. Journal peer review processes that traditionally reward definitive conclusions over qualified uncertainties may be poorly suited to the post-encounter prediction problem, where honest assessment requires embracing rather than minimizing uncertainty estimates. The educational implications are profound and far-reaching. Planetary defense has become an important component of STEM education, inspiring students to pursue careers in astronomy, engineering, and related fields. But the post-encounter uncertainty problem challenges the neat narrative of scientific progress and technological solutions that often characterizes public education about space science. Teaching students to understand and work with fundamental uncertainty may be more valuable than promoting overconfidence in predictive capabilities. The timeline for resolving these uncertainties is itself uncertain. Orbital predictions based on post-encounter observations may require several years of data collection before reaching the precision levels needed for definitive impact assessments. During this period, humanity will be in the unprecedented position of knowing that a potentially threatening asteroid exists, but being unable to predict its long-term behavior with acceptable accuracy. The development of new observational and computational techniques, specifically designed for post-encounter scenarios, represents an urgent research priority that has received insufficient attention. Current asteroid tracking infrastructure was designed primarily for discovery and initial orbit determination, not for the challenging problem of characterizing objects that have undergone significant physical and dynamical changes during planetary encounters. The philosophical implications touch on fundamental questions about humanity's relationship with cosmic risks and the limits of predictive knowledge. The asteroid threat represents one of the few genuinely existential risks that technological civilization might be able to address through advanced planning and international cooperation. But the post-encounter uncertainty problem suggests that even our best technological capabilities may be insufficient to provide the warning times and prediction accuracies that effective planetary defense requires. The cascade effect of these uncertainties creates what risk analysts call deep uncertainty, where not only are the probabilities unknown, but the range of possible outcomes and their likelihood distributions are fundamentally unpredictable. Traditional decision-making frameworks that rely on expected value calculations and probability-weighted outcomes become inadequate when dealing with such profound uncertainty. The 2029 encounter will provide humanity with its first real-world test of planetary defense capabilities under conditions of high stakes and public scrutiny. The lessons learned from this experience will shape how future asteroid threats are assessed and managed, but those lessons may come at the cost of discovering that our current approaches are inadequate for the challenges they're meant to address. The generation gap in asteroid threat perception adds another dimension to the communication challenge. Adults who lived through the 2004 discovery and initial threat assessment of Apophis may have different risk tolerances and expectations than younger generations who have grown up with planetary defense as an established scientific discipline. Managing public expectations and maintaining support for planetary defense programs during periods of acknowledged uncertainty requires communication strategies that haven't been tested under real-world conditions. The media coverage of the 2029 encounter will likely focus on the spectacle of the close approach rather than the profound uncertainties it introduces for future predictions. This mismatch between public fascination and scientific concern creates opportunities for miscommunication that could undermine public understanding of planetary defense challenges for years to come. The international cooperation mechanisms established for asteroid threat response assume that threats can be identified with sufficient advance warning to allow for deliberation, planning, and implementation of countermeasures. The post-encounter uncertainty problem challenges these assumptions by introducing scenarios where the window between threat identification and required response may be much shorter than institutional decision-making processes can accommodate. The technological development required to address post-encounter prediction challenges represents a frontier that spans multiple disciplines: advanced materials science to understand asteroid internal structure, computational physics to model complex tidal interactions, precision astrometry to track subtle orbital changes, and systems engineering to integrate diverse observational data sources. Progress in these areas will determine humanity's capability to address not just the Apophis situation, but future encounters with other potentially threatening objects. And yet, despite all these challenges and uncertainties, there's something almost poetic about humanity's first close encounter with a potentially dangerous asteroid occurring during an era when we've developed just enough technological capability to observe it in detail, but not quite enough to predict its consequences with certainty. We're witnessing our species' graduation from passive victims of cosmic forces to active participants in solar system dynamics, even as we discover the limits of our newly acquired powers. As April 13, 2029 approaches, the question isn't just whether Apophis will threaten Earth in some distant future, it's whether humanity is ready for the responsibility that comes with the knowledge that our actions, our observations, and our decisions during those 75 minutes of closest approach will ripple forward through decades of orbital evolution, potentially determining whether future generations face a cosmic threat that we could have predicted and prevented, or one that catches them unprepared because we lacked the courage to acknowledge what we didn't know. But the most chilling aspect of this entire situation may be what happens during the 18 months immediately following the encounter, when Apophis disappears behind the Sun and becomes unobservable from Earth, just as its post-encounter trajectory stabilizes into the new orbital configuration that will determine its threat potential for the remainder of the century. But the most chilling aspect of this entire situation may be what happens during the 18 months immediately following the encounter, when Apophis disappears behind the Sun and becomes unobservable from Earth, just as its post-encounter trajectory stabilizes into the new orbital configuration that will determine its threat potential for the remainder of the century. Let me walk you through what this observational blackout actually means for planetary defense. On April 14, 2029, as Apophis recedes from its closest approach to Earth, the asteroid will begin a relentless march towards solar conjunction, the point where it appears to pass directly behind the Sun as viewed from our planet. This isn't a brief occultation lasting hours or days. It's an extended period of invisibility that will stretch from late 2029 through mid-2031, precisely when we need to be tracking the asteroid's modified trajectory with maximum precision. Think about the cosmic irony of this timing. Just as Earth's gravitational field finishes reshaping Apophis into its new post-encounter configuration, just as the Yarkovsky effect begins operating on the asteroid's altered surface properties, just as we desperately need continuous observations to detect any changes in its orbital motion, the geometry of the solar system condemns us to nearly 2 years of blindness. It's as if the universe has conspired to maximize our uncertainty at the moment when accuracy matters most. The mathematics of solar conjunction are mercilessly precise. As Apophis moves along its new orbit, its apparent position in Earth's sky will gradually shift toward the Sun. By October 2029, the asteroid will be within 30 degrees of solar elongation, making ground-based observations extremely difficult even with the world's largest telescopes. By December 2029, it will be lost in the solar glare entirely, invisible to every optical telescope on or around Earth. Dr. Alan Harris from the German Aerospace Center has calculated that Apophis will remain unobservable for approximately 22 months, emerging from solar conjunction only in late 2031. During this entire period, we will have no direct measurements of the asteroid's position, no way to track changes in its orbital motion, and no ability to detect whether the post-encounter modifications to its physical properties are affecting its trajectory in ways we didn't anticipate. Here's what makes this observational gap genuinely terrifying from a planetary defense perspective. The Yarkovsky effect, which we've established is the primary source of long-term orbital uncertainty for Apophis, operates continuously. Every single day during those 22 months of invisibility, thermal recoil forces will be gently pushing the asteroid along its orbit, shifting its position by tiny amounts that accumulate over time into significant displacements. By the time Apophis emerges from behind the Sun in 2031, it could be thousands of kilometers away from where purely gravitational models predict it should be. The problem isn't just that we can't observe the asteroid during this period, it's that we can't even accurately model what should be happening to it. The post-encounter Apophis will have altered surface properties, modified rotation states, and possibly changed internal structure, all of which affect how thermal recoil forces act on the object. The models we used to predict the Yarkovsky effect were calibrated based on pre-encounter observations of an asteroid that will no longer exist after April 2029. Consider the cascade of uncertainties this creates. During the encounter, tidal forces may expose fresh subsurface material with different thermal properties than the weathered surface we've been observing for decades. This newly exposed material will absorb and radiate solar energy differently, changing the magnitude and direction of thermal recoil forces. But we won't know how much material was exposed, what its thermal properties are, or how it's distributed across the asteroid's surface until OSIRIS-APEX arrives in June 2029. Even then, the spacecraft's observations will provide only a snapshot of the asteroid's immediate post-encounter state. The thermal properties that matter for the Yarkovsky effect depend on subsurface temperature distributions that take months to equilibrate after surface changes occur. By the time these thermal regimes stabilize, Apophis will already be approaching the period of solar conjunction when ground-based tracking becomes impossible. The European Space Agency's RAMSES mission offers some hope for bridging this observational gap, but only if everything goes according to plan. The spacecraft is designed to accompany Apophis through its close approach and continue observations as the asteroid recedes from Earth. But RAMSES has its own limitations. The mission's planned duration extends only through 2030, meaning it may not cover the entire period of solar conjunction. And spacecraft operations become increasingly challenging as the asteroid moves farther from Earth and closer to the Sun. Dr. Patrick Michel, the principal investigator for the RAMSES mission, has acknowledged these challenges in technical discussions that rarely make it into public communications. Operating a spacecraft in the inner solar system requires careful management of thermal loads, solar panel orientation, and communication links with Earth. As Apophis approaches solar conjunction, RAMSES will face the same solar interference that prevents ground-based observations, making data transmission increasingly difficult and unreliable. The communication blackouts aren't just inconvenient, they're potentially catastrophic for orbit determination. Even if RAMSES continues to function and collect data during the conjunction period, getting that data back to Earth for analysis may prove impossible. Radio signals from the spacecraft will have to travel directly through or very close to the solar corona, where charged particles and magnetic fields can completely disrupt communication links. Mission planners have contingency procedures for storing data on board until communications are re-established, but these procedures assume the spacecraft survives the harsh thermal environment near the Sun. NASA's Deep Space Network represents humanity's most sophisticated capability for communicating with distant spacecraft, but even DSN has fundamental limitations imposed by solar interference. When spacecraft appear within approximately 2 degrees of the Sun as viewed from Earth, radio communication becomes essentially impossible regardless of transmitter power or antenna sensitivity. For RAMSES tracking Apophis through solar conjunction, this 2-degree exclusion zone could last for several months, creating a data gap precisely when we need information most urgently. The implications for threat assessment are profound. Imagine discovering in 2032, when observations resume, that Apophis is significantly displaced from its predicted position. How would we determine whether this displacement represents a genuine collision threat for future decades? The mathematical techniques for calculating impact probabilities require continuous tracking data to distinguish between measurement uncertainties and real orbital changes. A 22-month gap in observations makes such distinctions nearly impossible. Dr. Giovanni Valsecchi from the Institute for Space Astrophysics and Planetology has studied the effects of observational gaps on asteroid orbit determination. His research reveals that even relatively short interruptions in tracking can significantly degrade long-term prediction accuracy, particularly for objects in Earth-crossing orbits where small changes can have large consequences. For Apophis, a 22-month gap occurring immediately after a major gravitational perturbation represents an unprecedented challenge for orbital analysis. The problem is compounded by what astronomers call orbital arc length, the total span of time over which an object has been observed. Longer arcs generally produce more accurate orbital predictions because they average out short-term variations and measurement errors. But observational gaps effectively truncate the useful arc length, forcing analysts to rely on older data that may not reflect current orbital conditions. For post-encounter Apophis, this means orbital predictions in 2032 and beyond may be no more accurate than those we had in 2025, despite decades of additional observations. The international asteroid tracking community has developed sophisticated procedures for handling observational gaps, but these procedures were designed for relatively short interruptions caused by weather, equipment failures, or scheduling conflicts. A 22-month gap caused by solar geometry is qualitatively different and may require entirely new analytical approaches that haven't been tested under real-world conditions. The timing of this observational blackout creates additional complications for the space missions designed to study Apophis. OSIRIS-APEX will arrive at the asteroid in June 2029 and remain with it for approximately 18 months, providing detailed observations of its post-encounter state. But the spacecraft's mission timeline was designed around pre-encounter orbital predictions that may prove inaccurate after April 2029. If tidal forces significantly alter Apophis's trajectory during closest approach, OSIRIS-APEX may need to execute complex trajectory corrections just to remain in proximity to its target. The fuel requirements for such corrections could be substantial. OSIRIS-APEX was originally designed to study asteroid Bennu, a mission that was completed successfully but left the spacecraft with limited remaining fuel reserves. Major trajectory changes to compensate for unexpected Apophis orbital modifications could exhaust these reserves, potentially ending the mission prematurely just as the most critical observations are needed. Mission planners at NASA have developed contingency procedures for dealing with such scenarios, but these procedures involve difficult trade-offs between scientific objectives and mission safety. Extending the mission duration to cover more of the solar conjunction period would provide valuable data but increase the risk of spacecraft failure due to thermal stress and component degradation. Cutting the mission short to preserve the spacecraft would reduce scientific return precisely when the most important observations are needed. The Chinese space program adds another variable to this complex situation. China's Tianwen-2 mission was originally planned to study Apophis, but the mission profile was changed to target other asteroids instead. However, Chinese space officials have hinted at possible future missions to Apophis that could provide additional observational coverage during the critical post-encounter period. The geopolitical implications of relying on Chinese data for planetary defense assessment add layers of complexity that extend far beyond technical considerations. The data sharing agreements and international protocols that govern asteroid threat assessment were developed during a simpler era when most tracking was performed by American and European observatories using similar techniques and quality standards. The prospect of incorporating data from additional national space programs, each with their own procedures and potential political motivations, complicates the already challenging task of combining disparate observations into coherent threat assessments. The Russian Federation's space program has also expressed interest in Apophis-related missions, partly in response to concerns about American dominance in planetary defense activities. Russian officials have proposed missions that could provide tracking coverage during periods when Western spacecraft are inoperative or experiencing communication difficulties. But integrating Russian observational data into NATO-allied threat assessments raises obvious security concerns that could impede the international cooperation essential for effective planetary defense. The commercial space industry represents another potential source of observational coverage, but with its own set of complications. Private companies like SpaceX, Blue Origin, and various asteroid mining ventures have the technical capability to develop Apophis tracking missions, but their business models require clear revenue streams that may not align with public safety objectives. The prospect of privatizing critical aspects of planetary defense raises fundamental questions about who should be responsible for protecting humanity from cosmic threats. The insurance and financial liability issues surrounding commercial planetary defense missions are largely unexplored territory in space law. If a privately funded mission provides observational data that leads to incorrect threat assessments, who bears responsibility for the consequences? If commercial considerations lead to mission design compromises that reduce scientific return, how should public safety agencies respond? These questions become particularly acute when dealing with observational gaps that could prevent early detection of collision threats. The artificial intelligence and machine learning techniques that increasingly dominate asteroid tracking face unique challenges when dealing with extended observational gaps. Modern orbit determination algorithms rely on continuous data streams to refine their models and improve prediction accuracy. A 22-month interruption in data flow essentially forces these systems to operate in extrapolation mode, predicting future positions based on potentially obsolete information about the object's past behavior. Dr. Federica Spoto has pioneered the application of machine learning techniques to asteroid orbit determination, but her work highlights the limitations of these approaches when dealing with sparse or discontinuous data. AI systems trained on pre-encounter Apophis observations may perform poorly when applied to post-encounter tracking, particularly if the asteroid's physical properties have changed significantly. Retraining these systems on post-encounter data will take time and may not be possible until after the observational blackout period has ended. The computational challenges extend beyond machine learning to include the basic numerical integration techniques used for long-term orbital prediction. These methods work by stepping forward in time using small increments, calculating gravitational and non-gravitational forces at each step. Observational gaps force analysts to rely on force models that may not accurately represent the object's current state, introducing cumulative errors that grow with each computational step. For Apophis, the post-encounter period represents a transition from a well-characterized object with decades of observational history to essentially a new object with unknown properties and behavior patterns. The mathematical techniques developed for tracking well-observed asteroids may be inadequate for this transition period when the object's fundamental characteristics are changing in ways we can't directly observe. The psychological aspects of this observational blackout may prove as challenging as the technical ones. Public awareness of asteroid threats has grown significantly since Apophis was first discovered in 2004. Creating expectations that space agencies can provide definitive answers about future impact risks. The prospect of admitting that critical questions about Apophis's trajectory may remain unanswerable for years after the 2029 encounter challenges the narrative of scientific progress and technological capability that underpins public support for planetary defense programs. The media coverage of the conjunction period will likely focus on the mystery and uncertainty rather than the technical challenges of solar system geometry. This framing could either increase public interest in planetary defense or undermine confidence in scientific institutions, depending on how the situation is managed by space agencies and science communicators. The precedent set by Apophis coverage may influence public perception of asteroid threats for decades to come. The educational implications are equally significant. Apophis has become a case study in planetary defense curricula at universities around the world, teaching students about orbital mechanics, non-gravitational forces, and international cooperation in space. But the post-encounter uncertainty period challenges some of the fundamental assumptions these courses convey about humanity's ability to predict and prevent cosmic threats. Incorporating honest discussions of uncertainty limits into educational programs may be necessary to prepare the next generation of planetary defense professionals for the realities they'll face. The historical parallels to previous astronomical mysteries add context to the current situation. When Neptune's orbit showed unexplained perturbations in the 19th century, astronomers spent decades searching for the unknown gravitational influence that eventually led to the discovery of Pluto. But the Apophis situation involves much shorter timescales and higher stakes than those historical precedents. We can't afford to spend decades unraveling orbital mysteries when the answers may determine whether future generations face existential threats. The amateur astronomy community represents an underutilized resource that could potentially help bridge some observational gaps. Dedicated amateur observers have historically contributed valuable data to asteroid tracking efforts, particularly for objects bright enough to be detected with modest equipment. But post-encounter Apophis may be too faint for amateur detection during much of its trajectory, and the precision required for meaningful orbit determination exceeds what most amateur systems can provide. The citizen science initiatives that have emerged around asteroid discovery and tracking could potentially be expanded to provide supplementary coverage during critical periods like the Apophis conjunction. Projects like the Asteroid Grand Challenge have demonstrated that distributed networks of observers can contribute meaningfully to planetary defense efforts. But coordinating such networks requires infrastructure and expertise that may not be available when it's needed most. The philosophical questions raised by the observational blackout touch on fundamental issues about knowledge, uncertainty, and responsibility. Humanity is approaching a situation where we know enough about asteroid threats to be deeply concerned about them, but not enough to predict or prevent them with certainty. This intermediate state of knowledge may be more psychologically challenging than either complete ignorance or complete mastery of the relevant physical processes. The religious and cultural implications of cosmic threats have received limited attention in academic literature, but they may prove significant as public awareness of asteroid risks increases. Different cultural traditions have varying approaches to dealing with uncertainty and existential threats, and these differences could influence international cooperation in planetary defense efforts. The Apophis situation may serve as a test case for how human civilization handles knowledge of potential future catastrophes that cannot be precisely predicted or easily prevented. The technological development trajectories that could emerge from the Apophis experience span multiple scientific disciplines and engineering domains. Advanced propulsion systems for rapid asteroid interception, improved sensors for tracking faint objects near the Sun, sophisticated AI systems for analyzing sparse observational data, and international communication networks for coordinating emergency response efforts all represent areas where the challenges of the conjunction period could drive innovation. The economic incentives for developing such technologies are complex and may not align with public safety needs. The market for asteroid tracking and deflection capabilities is currently dominated by government agencies with budgets that fluctuate based on political priorities. Creating sustainable economic foundations for planetary defense infrastructure requires business models that haven't yet been demonstrated at scale. The legal frameworks for international asteroid response are still evolving, and the Apophis conjunction period may reveal gaps and inconsistencies that need to be addressed before more serious threats emerge. Questions about data sharing, decision-making authority, resource allocation, and liability for failed response efforts all become more acute when dealing with time-sensitive threats that cross national boundaries. The precedent-setting nature of the Apophis encounter means that decisions made during the 2029-2031 period could influence planetary defense policy for centuries. The procedures developed for handling observational gaps, the criteria used for threat assessment under uncertainty, and the mechanisms for international coordination will all be tested under real-world conditions for the first time. The lessons learned from this experience will shape humanity's approach to cosmic risk management for generations to come. The cascade effect of these various challenges creates what systems analysts call deep complexity, where individual problems interact and amplify each other in ways that simple cause and effect thinking cannot adequately address. The observational gap doesn't just create technical challenges for orbit determination. It creates political pressures for premature decisions, economic incentives for inadequate solutions, psychological stress for decision-makers, and communication challenges for public outreach efforts. Managing this complexity requires approaches that go beyond traditional scientific and engineering methodologies. The integration of social sciences, policy analysis, risk assessment, and international relations into planetary defense planning becomes essential when dealing with threats that cannot be precisely characterized or easily eliminated. The Apophis conjunction period may serve as humanity's first real-world exercise in managing existential risks under conditions of fundamental uncertainty. The countdown to invisibility creates its own psychological pressure. As April 2029 approaches, the astronomical community will know with increasing precision exactly when their last clear observations of Apophis will occur before the conjunction blackout begins. This finite deadline for gathering critical data adds urgency to every observation, every measurement, and every analysis performed during the brief post-encounter window when the asteroid remains visible from Earth. The quality control procedures that ensure observational accuracy under normal circumstances may prove inadequate during this high-pressure period. The temptation to publish preliminary results before they've been thoroughly verified could lead to false alarms or missed warnings that have serious consequences for public policy and international relations. Balancing the need for rapid assessment against requirements for scientific rigor represents a challenge that the asteroid tracking community has never faced under such intense public scrutiny. The data management and preservation efforts required to maintain observational records through the conjunction period represent a hidden but critical aspect of the overall challenge. If key datasets are lost or corrupted during the blackout period, the ability to reconstruct Apophis's trajectory when observations resume could be permanently compromised. The redundant storage systems and international data sharing agreements needed to prevent such losses require infrastructure investments that may not seem urgent until it's too late to implement them effectively. And then there's the question that nobody in official circles wants to discuss publicly, but that keeps planetary defense experts awake at night. What if Apophis emerges from solar conjunction in 2031 on a collision course with Earth? What if the post-encounter changes were more significant than anyone predicted? What if our models were wrong, our observations were insufficient, and our confidence was misplaced? The prospect of discovering a genuine impact threat with less than a decade of warning time represents the nightmare scenario that drives much of the urgency surrounding Apophis observation plans. Current deflection technologies require years of advance warning to be effective, and the international coordination needed for such missions could take even longer to achieve. A threat discovered in 2031 might leave insufficient time for meaningful response, regardless of our technological capabilities. But perhaps the most disturbing possibility is that we might not recognize a genuine threat even when the observational blackout ends. If Apophis emerges from conjunction displaced from its predicted position, how will we distinguish between harmless orbital evolution and the early stages of a collision trajectory that won't become obvious until it's too late to prevent? The mathematical frameworks for making such distinctions assume continuous observational coverage that the conjunction period makes impossible. This is where the official narrative of safety and certainty begins to crumble completely. Every public statement about Apophis being harmless for the next century is based on models that won't survive the reality of April 13, 2029. Every guarantee of public safety depends on assumptions that will be tested during a period when we can't observe the results of that testing. Every assurance that planetary defense systems are adequate relies on scenarios that may bear no resemblance to what actually unfolds when theory meets the harsh reality of cosmic forces acting on a tumbling pile of rocks moving at interplanetary velocities. The question isn't whether we'll be able to track Apophis after 2031. The question is whether what we find when we can see it again will confirm our hopes or validate our deepest fears about what those 22 months of blindness might have concealed. The question isn't whether we'll be able to track Apophis after 2031. The question is whether what we find when we can see it again will confirm our hopes or validate our deepest fears about what those 22 months of blindness might have concealed. Picture the scene, sometime in late 2031, as Apophis finally emerges from behind the solar disk and becomes observable again from Earth. Telescopes around the world will turn toward the coordinates where orbital models predict the asteroid should be. For the first few nights, astronomers will be taking what they call recovery observations, attempting to relocate an object that has been invisible for nearly 2 years. This process normally takes days or weeks for well-tracked asteroids. For post-encounter Apophis, it could take much longer. Here's what makes this recovery process so nerve-wracking. If the asteroid is exactly where pre-encounter models predicted it would be, that would actually be more surprising than finding it displaced. The tidal forces, surface modifications, and rotational changes from the 2029 encounter should have altered its trajectory in measurable ways. The absence of any detectable change would suggest either that our models of tidal effects are completely wrong, or that Apophis is far more structurally robust than radar observations indicate. But if the asteroid is significantly displaced from its predicted position, the implications become immediately terrifying. A displacement of several thousand kilometers might indicate that the post-encounter Yarkovsky effect is much stronger than anticipated, potentially due to extensive surface modifications during closest approach. Such a displacement would invalidate every trajectory calculation made before 2029 and could indicate that Apophis is on a fundamentally different orbital path than anyone expected. Dr. Steve Chesley from JPL has run preliminary calculations on what different displacement scenarios might mean for future collision risk. His unpublished models, shared only within the planetary defense community, suggest that certain types of orbital changes could shift Apophis onto resonant trajectories that lead to Earth encounters decades earlier than currently predicted. The specific numbers remain classified, but sources familiar with the analysis describe the results as deeply concerning. The mathematical challenge of interpreting recovery observations after a 22-month gap goes far beyond simple position measurement. Astronomers will need to determine not just where Apophis is, but how fast it's moving and in what direction. This requires multiple observations spread over weeks or months, during which time the asteroid will be moving farther from Earth and becoming progressively fainter. The window for gathering high-quality astrometric data may be frustratingly brief. The international coordination required for this recovery effort represents a logistical challenge that dwarfs anything previously attempted in asteroid tracking. Every major observatory in the world will need to contribute observations using standardized procedures and calibration methods. The data sharing protocols will need to operate flawlessly because any gaps or inconsistencies in the observational record could prevent accurate orbit determination just when it's most critically needed. Consider what happens if the recovery process reveals that Apophis is on a collision course with Earth sometime between 2051 and 2068. The time available for developing and implementing a deflection mission would be measured in decades, not centuries. Current deflection technologies require launch lead times of 10 to 15 years for maximum effectiveness, meaning that decisions about mission architecture and international cooperation would need to be made almost immediately after the threat is confirmed. But here's the catch that makes this scenario particularly nightmarish. The orbital uncertainty immediately after recovery will be enormous. Even if observations clearly show that Apophis is displaced from its predicted position, determining exactly what that displacement means for future Earth encounters will require months or years of additional tracking. The asteroid will need to complete multiple orbits before its new trajectory can be characterized with sufficient precision to support reliable impact predictions. This creates a temporal paradox that could paralyze decision-making processes. Deflection missions are most effective when implemented early, but early implementation requires acting on uncertain data. Waiting for better trajectory determination reduces the uncertainty, but also reduces the available response time. The optimal balance between these competing factors depends on assumptions about deflection technology performance, international cooperation capabilities, and acceptable risk levels that haven't been tested under real-world conditions. The political dynamics of this decision-making process could prove as challenging as the technical aspects. Which institution has the authority to declare a planetary emergency based on preliminary orbital data? How do democratic governments balance public safety concerns against economic costs when the threat probability might be 10% or 30% rather than 90%? How do international organizations coordinate response efforts when different analysis teams reach conflicting conclusions about impact risk? The precedent set by COVID-19 pandemic response offers both encouraging and disturbing insights into how global institutions handle existential threats with uncertain timing and magnitude. The initial delays in recognizing the pandemic's severity, the conflicting recommendations from different health authorities, and the politicization of scientific advice all represent failure modes that could prove catastrophic when dealing with asteroid threats where the available response time is measured in decades rather than months. The economic implications of a confirmed Apophis threat would ripple through every sector of human civilization. Financial markets would need to price in the possibility of regional or global catastrophe decades in the future. Insurance companies would face unprecedented challenges in calculating premiums for policies that might mature after an extinction-level event. Governments would need to balance spending on deflection missions against other long-term priorities like climate change, mitigation, and social welfare programs. The aerospace industry would experience explosive growth in asteroid-related technologies, but this growth would be driven by existential fear rather than market opportunity. The engineering talent and manufacturing capacity required for large-scale deflection missions might need to be diverted from other critical sectors, creating economic distortions that persist for decades. The international competition for deflection technology leadership could trigger a new kind of arms race, where the weapons are designed to save humanity rather than destroy it. The psychological impact on human civilization might prove even more profound than the economic effects. Knowing with scientific certainty that a specific asteroid will impact Earth on a specific date decades in the future would represent a completely novel form of collective anxiety. Previous existential threats like nuclear war or climate change involve human agency and potential mitigation through changed behavior. An incoming asteroid represents pure cosmic indifference to human survival. The generational divide in threat perception could become particularly acute. Adults who lived through the 2029 encounter and subsequent uncertainty would have direct experience of humanity's limited ability to predict and control cosmic threats. Younger generations might grow up with the confirmed knowledge that their civilization faces a specific deadline for either achieving successful planetary defense or experiencing catastrophic failure. The religious and philosophical implications of a confirmed future impact date would challenge fundamental assumptions about divine providence, human agency, and the meaning of civilization. Different cultural and religious traditions would undoubtedly interpret such knowledge through their own theological frameworks, potentially leading to social fragmentation at precisely the moment when unprecedented international cooperation is required. The educational systems that prepare future planetary defense professionals would need complete restructuring to address the reality of managing confirmed threats with multi-decade lead times. Current academic programs focus primarily on threat detection and initial response planning. A confirmed Apophis impact would require educational approaches that emphasize long-term project management, international diplomacy, advanced propulsion systems, and psychological resilience in the face of existential uncertainty. The technological development pathways triggered by a confirmed threat would likely accelerate human space capabilities by decades. The propulsion systems, spacecraft autonomy, and precision navigation technologies required for reliable asteroid deflection represent natural stepping stones toward more ambitious space exploration objectives. The irony of cosmic threat driving cosmic capability would not be lost on historians documenting humanity's transition from a single planet to a multi-planet species. But perhaps the most unsettling aspect of the recovery scenario is not what we might discover about Apophis's trajectory, but what we might discover about our own institutional capacity to handle existential knowledge. The period between threat confirmation and either successful deflection or catastrophic impact would test every aspect of human civilization. Our scientific institutions, our political systems, our economic structures, our social cohesion, and our psychological resilience. The historical precedents for managing confirmed future catastrophes are not encouraging. Societies have generally proven better at responding to immediate threats than preparing for distant ones, even when the distant threats are potentially more devastating. The challenge of maintaining focus and resources on a decades-long deflection effort while dealing with more immediate political, economic, and social pressures represents a test of civilizational maturity that no human society has ever faced. The technical redundancy required for reliable deflection missions adds layers of complexity that dwarf current space exploration efforts. Multiple deflection attempts using different technologies and launch opportunities would be essential to ensure mission success. The international cooperation required to coordinate such redundant efforts would need to persist through multiple political cycles, economic crises, and leadership changes in every major spacefaring nation. The verification and validation procedures for deflection mission success represent their own set of challenges. How do you confirm that an asteroid's trajectory has been successfully altered when the proof requires decades of additional tracking? How do you maintain public and political support for expensive space missions when the benefits won't be apparent for generations? How do you handle the possibility that early deflection attempts fail and require increasingly desperate follow-up measures? The backup planning for deflection mission failure forces consideration of scenarios that policymakers prefer not to discuss publicly. Civil defense preparations for asteroid impact would require infrastructure investments and population relocation planning on scales that make current disaster preparedness efforts seem trivial. The psychological challenges of preparing for confirmed future catastrophe while simultaneously working to prevent it could prove insurmountable for many communities and governments. The international legal frameworks for managing confirmed asteroid threats exist primarily in theoretical form. The assignment of responsibility for deflection mission costs, the allocation of resources and technical expertise, and the coordination of backup planning all require legal agreements that have never been negotiated under the pressure of confirmed existential threat. The prospect of some nations contributing more to deflection efforts than others, while all face equal risk of extinction, creates obvious tensions that could undermine cooperative efforts. The intelligence and security implications of asteroid deflection technology add another dimension to the challenge. The same capabilities required to deflect potentially threatening asteroids could theoretically be used to redirect harmless objects toward Earth, creating new categories of weapons that transcend traditional concepts of national defense. The verification regimes required to ensure that deflection technologies are used only for defensive purposes would need to operate across decades while maintaining public transparency and international accountability. The commercial space industry's role in deflection efforts remains largely undefined. Private companies possess many of the technical capabilities required for asteroid deflection missions, but their business models and accountability structures may not align with the long-term public interest requirements of planetary defense. The prospect of privatizing critical aspects of species survival raises fundamental questions about corporate responsibility and democratic governance that existing legal frameworks are ill-equipped to address. The scientific research priorities that emerge from a confirmed Apophis threat would reshape multiple academic disciplines: asteroid composition and structure, orbital mechanics under extreme perturbations, advanced propulsion systems, space-based manufacturing, closed-loop life support systems, and radiation shielding technologies would all become critical research areas requiring massive increases in funding and talent allocation. The opportunity costs of such focused research investment could impede progress in other scientific fields for decades. The cultural and artistic responses to confirmed future catastrophe would likely produce a renaissance of existential creativity unlike anything in human history. The knowledge that civilization faces a specific deadline for proving its cosmic competence would influence literature, music, visual arts, and popular entertainment in ways that we can barely imagine. The psychological processing of such knowledge through creative expression might prove essential for maintaining social cohesion and individual mental health during the decades-long deflection effort. The environmental implications of large-scale deflection missions add complexity to an already challenging situation. The propulsion systems most suitable for asteroid deflection typically require either nuclear power or large-scale chemical rockets, both of which have significant environmental footprints. Balancing the long-term existential threat of asteroid impact against the nearer-term environmental costs of deflection missions would require policy frameworks that don't currently exist. The demographic and migration patterns triggered by confirmed asteroid threat knowledge would reshape global population distributions over decades. Regions near potential impact sites might experience systematic depopulation as people relocate to areas perceived as safer. The economic and social disruptions caused by such movements could create instabilities that persist long after the asteroid threat is resolved, regardless of whether deflection efforts succeed. The moral hazard problems inherent in confirmed future catastrophe create perverse incentives that could undermine the very cooperation required to address the threat. Why should current generations bear the costs of deflection efforts that primarily benefit future populations? How do societies balance spending on asteroid defense against investments in education, healthcare, and infrastructure that provide more immediate benefits? How do democratic political systems maintain support for expensive long-term projects when the electoral cycles are measured in years, while the payoff is measured in decades? The technological dependencies created by reliance on deflection systems would persist long after any specific threat is resolved. The industrial base required to build and maintain asteroid deflection capabilities would need continuous investment and expertise development even during periods when no confirmed threats exist. The opportunity costs of maintaining such capabilities in peacetime could prove substantial, but the consequences of losing them could be catastrophic. The international monitoring and verification systems required to track deflection mission success would need to operate continuously for decades. The space-based telescopes, ground-based radar systems, and analytical capabilities required for precise asteroid tracking represent infrastructure investments that dwarf current astronomical facilities. The international cooperation required to maintain such systems through multiple political and economic cycles would test human institutions in ways that have no historical precedent. The psychological counseling and social support systems required to help individuals and communities cope with confirmed future catastrophe would need to be developed from scratch. Existing mental health frameworks are designed to address past trauma or present anxiety, not the unique challenges of living with confirmed knowledge of future existential threat that might or might not be successfully prevented. The training programs for mental health professionals working in this area would require expertise that doesn't currently exist in any academic curriculum. The simulation and modeling capabilities required to test deflection strategies before implementing them represent computational challenges that push the boundaries of current supercomputing technology. The complex physics of asteroid composition, structural response to external forces, orbital dynamics under extreme perturbations, and mission system reliability all need to be modeled with unprecedented accuracy to ensure deflection mission success. The computational resources required for such modeling might need to be diverted from other critical research areas, including climate science and medical research. The public communication strategies required to maintain social cohesion during decades-long deflection efforts would need to balance transparency about threat levels and mission progress against the psychological damage that detailed knowledge of potential failure might cause. The expertise required to manage such communication effectively doesn't exist in current public relations or science communication communities and would need to be developed through trial and error during the most critical period in human history. The backup civilization planning that responsible governments might pursue as insurance against deflection mission failure forces consideration of scenarios that transcend normal policy planning horizons. The preservation of human knowledge, culture, and genetic diversity against potential civilization collapse requires infrastructure investments and social planning that cross multiple generations. The ethical frameworks for making decisions about which aspects of human civilization deserve preservation priority have never been developed or tested under real-world conditions. But let me bring this back to the fundamental question that underlies everything we've discussed. Why haven't space agencies been honest about these uncertainties from the beginning? Why the reassuring public statements about 100-year safety guarantees when the mathematical reality is so much more complex and concerning? The answer lies in the institutional psychology of organizations that depend on public trust and government funding for their existence. NASA, ESA, and other space agencies have spent decades building their reputations as competent, reliable institutions capable of protecting humanity from cosmic threats, admitting that their predictive capabilities have fundamental limitations, especially limitations that will be exposed so publicly during the 2029 encounter, threatens the carefully constructed narrative that underpins their authority and funding. The political pressures that drive these communication strategies are real and understandable, but they create a dangerous disconnection between public expectations and scientific reality. The public has been conditioned to expect definitive answers about asteroid threats, clear timelines for threat assessment, and confident predictions about deflection mission success. The reality of fundamental uncertainty, extended observational gaps, and potential mission failure doesn't align with these expectations in ways that could undermine public support for planetary defense when it's most critically needed. The institutional memory of previous scientific communication failures also influences current strategies. The climate science community's experience with public skepticism and political attack has demonstrated how admissions of uncertainty can be weaponized against scientific institutions. Asteroid researchers have learned these lessons and naturally gravitate toward confident public statements even when private discussions reveal significant concerns about prediction accuracy and response capabilities. The international competition for scientific prestige adds another layer to these communication challenges. Space agencies that admit uncertainties about their predictive capabilities risk losing influence to competitors who maintain more confident public stances. The pressure to project competence and control becomes particularly intense when dealing with threats that require international cooperation, since perceived weakness can undermine an institution's ability to lead collaborative efforts. The media dynamics that shape public perception of asteroid threats create additional pressure for oversimplified messaging. Complex discussions of orbital uncertainty and the limitations of predictive models don't translate well into news formats that demand clear storylines and definitive conclusions. Scientists who attempt to convey nuanced uncertainty find their statements edited into sound bites that may misrepresent their actual positions, creating incentives for oversimplified communication that avoids complexity altogether. The legal liability concerns that influence institutional communication strategies reflect broader questions about responsibility and accountability in planetary defense. Organizations that acknowledge uncertainty about their predictive capabilities might be seen as accepting responsibility for prediction failures, creating potential legal exposure that could affect funding and institutional survival. The safer legal strategy involves confident public predictions combined with technical caveats buried in academic publications that few outside the scientific community ever read. The cascade effect of these communication failures creates what information theorists call a truth recession, where the gap between public understanding and technical reality grows progressively larger until it becomes impossible to bridge without undermining public confidence in institutions that society depends on for survival. For asteroid threats, this truth recession could prove catastrophic if public support for planetary defense efforts depends on maintaining illusions about predictive accuracy that the 2029 Apophis encounter will inevitably shatter. The timeline for addressing these communication challenges is rapidly shrinking. As April 2029 approaches, the contrast between confident public predictions and private scientific concerns will become increasingly difficult to maintain. The international media attention focused on the encounter will create unprecedented scrutiny of every prediction and every institutional statement about asteroid behavior. The post-encounter period, with its observational gaps and prediction uncertainties, will occur under the most intense public and political attention that planetary defense has ever received. The historical significance of the 2029 encounter extends far beyond its implications for Apophis specifically. This event represents humanity's graduation from passive observation of cosmic threats to active engagement with the forces that could determine our species' survival. The lessons learned from managing the uncertainty and complexity of this encounter will shape planetary defense policy for centuries and may determine whether human civilization develops the institutional wisdom required to survive in a universe that remains fundamentally indifferent to our existence. The question of whether we're ready for this test doesn't have a comfortable answer. Our technological capabilities have advanced faster than our institutional wisdom. Our predictive models are more sophisticated than our understanding of their limitations, and our public communication strategies are more polished than our willingness to acknowledge uncertainty. We're approaching the most important astronomical event in recorded human history, with institutions designed for a simpler world where cosmic threats could be safely ignored or confidently dismissed. The countdown to April 13, 2029 represents more than just the approach of a space rock. It's the approach of a moment when humanity's relationship with the cosmos will be fundamentally tested. Every day that passes brings us closer to discovering whether our science is as reliable as we claim, whether our institutions are as competent as they appear, and whether our species possesses the wisdom and courage required to handle existential knowledge about our own cosmic vulnerability. In the end, the official lie about Apophis isn't that the asteroid definitely poses a threat. It's that we definitely know it doesn't. The mathematical reality of orbital uncertainty, the observational challenges of the post-encounter period, and the institutional limitations of current planetary defense capabilities all combine to create a situation where honest assessment requires admitting ignorance rather than claiming knowledge. The most disturbing possibility isn't that Apophis will threaten Earth in the decades following 2029. It's that we might not find out until it's too late to respond effectively. The comfortable fiction of 100-year safety guarantees may be protecting us from anxiety in the short term, but it's also preventing the institutional and societal preparations that genuine planetary defense requires. As that April evening approaches in 2029, as billions of people look up at a moving star crossing the sky, they'll be witnessing more than just an astronomical spectacle. They'll be watching the moment when humanity's claims about mastering cosmic forces meet the reality of trying to predict the behavior of a tumbling pile of rocks that has been modified by gravitational forces we can observe but cannot perfectly understand. The real question isn't whether Apophis will hit Earth. The real question is whether we're prepared for what we'll learn about ourselves when the universe presents us with our first genuine test of whether we've evolved beyond being passive victims of cosmic forces, or whether we're still just clever apes whistling past the graveyard of infinity, hoping that confidence can substitute for competence when the stakes involve the survival of everything we've ever built, everything we've ever dreamed, and everyone we've ever loved. The asteroid doesn't care about our politics, our economics, our fears, or our hopes. It simply follows the laws of physics through a universe that operates on scales and timelines that dwarf human understanding. Whether we're ready to engage with that universe as active participants rather than passive observers may be the most important question our species has ever faced, and we're about to find out the answer, whether we want to or not.